Have you ever wondered what secrets Earth might be hiding in its deepest layers? What if everything we think we know about our planet's history is just scratching the surface of something far more extraordinary? Tonight, we're going to explore one of the most fascinating questions that scientists are beginning to ask seriously. Could an advanced civilization have existed millions of years before the first dinosaur ever walked the earth? Close your eyes and imagine this. You're standing on a beach picking up grains of sand. Each grain represents 1,000 years of human history. Now, if you were to collect enough sand to fill an entire football stadium, that would barely represent the time that has passed since complex life first appeared on our planet. This is the scale we're dealing with when we talk about deep time. And it's in these vast, almost incomprehensible stretches of history that our story begins. We often think of ourselves as the pinnacle of intelligence on Earth, the first species to develop language, build cities, and reach for the stars. But what if that assumption is fundamentally flawed? What if we're not the beginning of the story, but simply the latest chapter in a much older book? Earth formed roughly 4.5 billion years ago. To put this in perspective, if our planet's entire history were compressed into a single day, humans wouldn't appear until the last few seconds before midnight. The dinosaurs, those ancient giants we consider so old, would only show up around 10:30 at night. That leaves nearly 22 hours of Earth's day completely unaccounted for in our understanding of intelligent life. During those early hours of Earth's metaphorical day, incredible things were happening. The atmosphere was forming, oceans were filling, and life was taking its first tentative steps. But here's where things get interesting. We've only been able to study a tiny fraction of what actually occurred during these vast periods. The fossil record, which we rely on so heavily to understand the past, is incredibly incomplete. Most life that has ever existed on this planet left no trace whatsoever. Think about this for a moment. For a creature to become fossilized, it needs to die in exactly the right place, at exactly the right time, under exactly the right conditions. Then, over millions of years, it must somehow survive earthquakes, volcanic eruptions, erosion, and the constant recycling of Earth's crust. The odds are astronomical. Most paleontologists estimate that we've discovered less than 1% of all species that have ever lived. But fossils aren't the only way to detect ancient life. Scientists have developed sophisticated techniques to read the chemical signatures left behind in rocks. These geological fingerprints can tell us about ancient atmospheres, climate changes, and even massive biological events. And sometimes they reveal patterns that don't quite fit our current understanding of how life developed on Earth. In recent years, a small but growing number of researchers have begun asking uncomfortable questions about these chemical signatures. Some unusual patterns in ancient rock layers show sudden spikes in certain elements, rapid changes in atmospheric composition, and other anomalies that are difficult to explain using conventional theories. While most of these can be attributed to natural processes like volcanic eruptions or asteroid impacts, a few remain mysteries. This brings us to what scientists call the Silurian hypothesis, named after a fictional ancient reptilian civilization from a popular science fiction series. But don't let the playful name fool you. This is serious science. The hypothesis doesn't claim that such a civilization existed, but rather asks a crucial question. If an advanced civilization had existed millions of years ago, would we be able to detect it today? The answer, according to researchers who have studied this question, is surprisingly complex. Our modern industrial civilization leaves behind numerous traces. We've altered the chemical composition of the atmosphere, deposited synthetic materials in sediment layers, and even created new isotopes through nuclear testing. But here's the sobering reality. Most of these markers would disappear relatively quickly on geological timescales. Consider what would happen if human civilization vanished tomorrow. Within a few thousand years, our cities would crumble, steel would rust, concrete would crack, and nature would reclaim our greatest achievements. Within 1,000,000 years, even our most durable constructions would be little more than chemical traces in rock layers, and within 10 million years, even those traces would be extremely difficult to detect. Now imagine looking for evidence of a civilization that existed not 1 million or 10 million years ago, but 300 million years ago. The land masses they lived on might no longer exist, swallowed up by tectonic processes and recycled into new rock formations. Any structures they built would have been ground to dust and scattered by geological forces beyond our comprehension. This doesn't mean such a civilization couldn't have existed. It simply means we need to look for different kinds of evidence. Instead of searching for ruins or artifacts, scientists are learning to read the subtle chemical stories written in ancient rocks. They're looking for patterns that suggest rapid environmental changes, unusual mineral concentrations, or disruptions in natural cycles that might indicate technological activity. One of the most promising avenues of research involves studying carbon isotopes in ancient sedimentary layers. When organic matter decomposes or burns, it leaves behind a specific chemical signature. Large-scale industrial activity would create patterns similar to what we're producing today through fossil fuel consumption. Several researchers have identified unusual carbon spikes in rocks from hundreds of millions of years ago, though the causes remain hotly debated. Another intriguing line of investigation focuses on rare earth elements and unusual metal concentrations in ancient geological formations. Modern industry requires specific materials that don't typically concentrate naturally. If an ancient civilization had developed similar technologies, they might have left behind detectable traces of mining, refining, or manufacturing activities. The challenge, of course, is distinguishing between natural processes and potential technological signatures. Earth has experienced countless volcanic eruptions, asteroid impacts, and other dramatic events throughout its history. Each of these can create chemical patterns that might superficially resemble industrial activity. This is why the search for ancient civilizations requires extraordinary care and rigorous scientific methodology. But what might such an ancient civilization have looked like? This is where we must abandon our preconceptions about intelligence and technology. We tend to assume that any advanced species would develop along similar lines to humans, building cities, using metals, and eventually reaching for space. But evolution doesn't repeat itself exactly. An intelligent species that arose hundreds of millions of years ago might have taken a completely different path. Perhaps they were aquatic, living in vast underwater cities that left no trace when the ocean floors were eventually recycled through subduction. Maybe they developed biological technologies, engineering living organisms instead of building machines. Or perhaps they achieved a level of harmony with their environment that we can barely imagine, leaving behind no permanent structures because they didn't need them. The more we learn about intelligence in the natural world, the more we realize how diverse it can be. Octopuses demonstrate remarkable problem-solving abilities and can use tools, yet they build nothing permanent. Dolphins have complex languages and cultural traditions, but leave no archaeological record. Even on Earth today, intelligence takes many forms, most of which would be invisible to future archaeologists. This raises profound questions about our own assumptions regarding technological development. We measure advancement by what civilizations leave behind, by their monuments and machines. But what if the most advanced civilizations are those that learn to live so efficiently, so sustainably, that they leave no trace at all? What if the absence of evidence isn't proof of absence, but rather a sign of wisdom we haven't yet achieved? As we continue this exploration, we'll delve deeper into the specific evidence that has scientists reconsidering Earth's deep history. We'll examine the chemical fingerprints that might betray ancient industry, the geological anomalies that don't quite fit our current models, and the tantalizing possibility that intelligence on our planet is far older and more cyclical than we ever imagined. The implications of this research extend far beyond academic curiosity. If Earth has hosted intelligent life before, it changes our understanding of evolution, consciousness, and our own place in the cosmic story. It suggests that the universe's capacity for creating complex thinking beings might be far greater than we currently believe. So settle in as we journey through deep time, exploring the shadows and whispers of civilizations that may have risen and fallen long before the first dinosaur drew breath. Tonight, we're not just learning about the past. We're questioning the very foundations of what we think we know about intelligence, consciousness, and the remarkable planet we call home. The deeper we venture into this mystery, the more we encounter what geologists call preservation bias. This concept fundamentally shapes how we interpret Earth's ancient past. Simply put, we can only study what has survived, and survival over hundreds of millions of years requires extraordinary circumstances. Imagine you're trying to understand a vast library, but 99% of the books have been destroyed by fire, flood, and time. The remaining volumes give you glimpses of knowledge, fragments of stories, but the complete picture remains frustratingly out of reach. This is precisely the challenge facing scientists who study deep time. Rock formations tell stories, but they're written in a language that's often difficult to decipher. Each layer represents thousands or millions of years of accumulated sediment, volcanic ash, or biological material. When we examine these layers, we're reading Earth's diary, page by page, but many pages have been torn out, burned, or rewritten by geological processes we're only beginning to understand. Consider the Precambrian era, which encompasses nearly 90% of Earth's entire history. This vast expanse of time stretches from our planet's formation until about 540 million years ago. During this period, life existed primarily as single-celled organisms, though toward the end, more complex creatures began to emerge. Yet our understanding of these eons remains remarkably limited. The few fossils we've discovered from this time period are mostly microscopic, preserved in rare formations where conditions happen to be just right. But what about the countless ecosystems that thrived and vanished without leaving any trace? What about the evolutionary experiments that succeeded for millions of years before disappearing completely? Recent discoveries have begun to challenge our assumptions about early life on Earth. Scientists have found evidence of complex bacterial communities that could manipulate their environment in sophisticated ways. These microbial mats could alter water chemistry, influence mineral formation, and even create structures that resembled primitive cities when viewed under powerful microscopes. If simple bacteria could engineer their surroundings millions of years ago, what might more complex organisms have achieved given enough time? Evolution doesn't move in straight lines. It explores countless possibilities, most of which lead to extinction, but some of which might have led to forms of intelligence we can barely imagine. The search for ancient technological signatures has led researchers to examine unusual mineral formations found in some of the world's oldest rock layers. These formations contain concentrations of elements that are difficult to explain through natural processes alone. While volcanic activity and hydrothermal vents can create complex chemical environments, some patterns suggest more organized, systematic processes. One particularly intriguing discovery involves microscopic spheres found in billion-year-old rock formations. These perfectly round objects show signs of having been manufactured rather than formed naturally. Their uniform size and composition have puzzled geologists for decades. Some researchers propose they're the result of unknown geological processes, while others wonder if they might be the remnants of ancient nanotechnology. The concept of nanotechnology existing billions of years ago might seem absurd, but consider this. Nature has been working at the molecular level for as long as life has existed. DNA is essentially biological nanotechnology, capable of storing vast amounts of information and executing complex instructions at the cellular level. If evolution could produce such sophisticated molecular machinery through natural selection, what might directed intelligence have achieved, given millions of years to develop? Another avenue of research focuses on isotopic anomalies in ancient rock layers. Isotopes are variants of chemical elements that have different numbers of neutrons in their atomic nuclei. Natural processes typically produce predictable ratios of different isotopes, but technological activities can alter these ratios in distinctive ways. Modern industrial processes leave clear isotopic signatures. Nuclear reactors, for example, produce specific isotopes that don't occur naturally in significant quantities. Similarly, large-scale chemical processing can alter the isotopic composition of elements like carbon, nitrogen, and sulfur in ways that persist for millions of years. Several research teams have identified unusual isotopic patterns in ancient geological formations. These anomalies are subtle and often dismissed as measurement errors or unknown natural processes. However, as analytical techniques become more sophisticated, some patterns are becoming difficult to explain without invoking some form of systematic, large-scale activity. The question isn't whether these anomalies prove the existence of ancient civilizations. Science doesn't work that way. Instead, researchers are trying to understand what processes could have created these patterns and whether any of those processes might have been biological or technological in origin. This brings us to one of the most fascinating aspects of this research, the realization that intelligence might not always leave the kinds of traces we expect. Our assumptions about technological development are based on our own experience, but there is no reason to believe that all intelligent species would follow the same path. Consider the possibility of biotechnology advanced far beyond anything we've achieved. Instead of building machines from metal and plastic, an ancient civilization might have engineered living organisms to serve technological functions. Biological computers, organic transportation systems, living buildings that could repair themselves and adapt to changing conditions. Such biotechnology would leave very different traces than our mechanical approach. Instead of metal oxides and synthetic polymers, we might find unusual organic compounds, modified genetic sequences, or biological structures that seem too complex to have evolved naturally. These traces would be much more difficult to detect and interpret, especially after hundreds of millions of years of decay and geological processing. The ocean floors present another compelling area of investigation. Most of Earth's surface water has been recycled countless times through evaporation and precipitation. But the deep ocean basins preserve chemical records spanning hundreds of millions of years. If ancient civilizations were primarily aquatic, their traces might be preserved in deep-sea sediments. Recent deep ocean drilling projects have revealed layers of sediment containing unusual chemical signatures. Some of these layers show evidence of rapid environmental changes that occurred over periods of just a few thousand years, incredibly brief intervals in geological terms. While most scientists attribute these changes to volcanic activity or climate shifts, a few researchers have noted that the patterns resemble what we might expect from large-scale technological activity. The possibility of aquatic civilizations opens up entirely new ways of thinking about intelligence and technology. Water-based life forms might develop technologies that work with fluid dynamics rather than solid mechanics. They might harness ocean currents for energy, use pressure differentials for manufacturing, or develop chemical processes that we land-dwelling creatures never considered. Archaeological evidence from underwater sites on our own planet shows how quickly the ocean can conceal and preserve human artifacts. Stone structures that would have eroded away on land can remain intact for thousands of years beneath the waves. But over millions of years, even the most durable underwater constructions would eventually be buried under layers of sediment or destroyed by tectonic activity. The challenge of detecting ancient aquatic civilizations highlights a crucial limitation in our search methods. We're looking for evidence using techniques and assumptions based on our own experience as terrestrial carbon-based life forms who developed metalworking and fossil fuel technologies. But intelligence might take forms so different from our own that we wouldn't recognize its signatures even if we found them. This limitation extends to our understanding of consciousness itself. We tend to equate intelligence with individual brains housed in discrete bodies. But nature demonstrates many other organizational structures. Fungal networks can span vast areas and exhibit decision-making behaviors that resemble intelligence. Ant colonies display collective problem-solving abilities that no individual ant possesses. Even bacterial colonies can exhibit coordinated responses to environmental challenges. What if ancient intelligence operated on scales and through mechanisms completely foreign to our experience? What if consciousness emerged not in individual organisms, but in vast, interconnected biological networks that spanned continents? Such intelligence might leave traces in the form of unusually organized mineral deposits, systematic changes in soil chemistry, or biological structures that seem too purposeful to have arisen through random evolutionary processes. The search for these alternative forms of ancient intelligence requires us to expand our definition of technology itself. Instead of looking only for the byproducts of industry and engineering, we might need to search for evidence of biological manipulation, environmental management, or even consciousness-based technologies that operate through principles we haven't yet discovered. As we continue our journey through these possibilities, we find ourselves confronting fundamental questions about the nature of intelligence, consciousness, and technological development. The answers we discover may not only reshape our understanding of Earth's deep history, but also challenge our assumptions about our own future and our place in the cosmic story of intelligence. The implications of these discoveries extend far beyond simple curiosity about our planet's past. They force us to reconsider the very nature of progress and development. We measure our own advancement by the complexity of our tools, the height of our buildings, the reach of our communications networks. But what if true advancement lies in the opposite direction? What if the most sophisticated civilizations are those that learn to achieve their goals with minimal environmental impact? This perspective transforms our understanding of what traces an advanced civilization might leave behind. Instead of looking for evidence of massive construction projects or industrial pollution, perhaps we should be searching for signs of remarkable efficiency. Patterns in ancient ecosystems that suggest careful management rather than exploitation. Chemical signatures that indicate sustainable energy use rather than resource depletion. Biological diversity that points to enhancement rather than destruction. The concept challenges our deepest assumptions about intelligence and ambition. We've built our entire understanding of progress on the idea that advancement means greater control over our environment, more complex technologies, larger populations supported by increasingly sophisticated systems. But what if this trajectory represents just one possible path among many? Now consider the possibility that an ancient civilization discovered principles of energy and matter manipulation that we haven't even begun to imagine. Physics tells us that the universe operates according to laws we're still uncovering. Quantum mechanics reveals phenomena that seem almost magical compared to our everyday experience. What if beings with millions of years to develop their understanding learned to work with forces and fields that remain completely unknown to us? Such advanced physics might enable technologies that operate without leaving conventional traces. Energy systems that tap directly into quantum fluctuations or zero-point fields. Transportation methods that manipulate space-time itself rather than pushing against it. Manufacturing processes that work at the atomic level, assembling materials from basic elements without the waste and pollution we associate with industry. These speculative technologies sound like fantasy, but they're based on real physics that we're only beginning to explore. Our current understanding of the universe is still remarkably limited. We know that dark matter and dark energy comprise most of reality, yet we have no idea what they actually are. We've discovered that empty space itself contains enormous amounts of energy, but we don't know how to access it. We've found that consciousness somehow collapses quantum wave functions, but we can't explain how or why. An ancient civilization with hundreds of millions of years to investigate these mysteries might have developed technologies so advanced that their operation would be indistinguishable from magic to our current understanding. They might have learned to manipulate consciousness itself as a fundamental force, using awareness and intention as tools for reshaping reality at the quantum level. This possibility opens up entirely new categories of evidence to search for in the geological record. Instead of looking for chemical pollution or structural remains, we might need to search for patterns that suggest reality itself was being systematically altered. Unusual quantum signatures in ancient crystals, mineral formations that seem to violate known laws of physics, biological fossils that show signs of having been modified at the genetic level in ways that natural evolution couldn't achieve. The challenge is that such evidence would be extremely subtle and difficult to interpret. We're only just beginning to develop instruments sensitive enough to detect quantum-level phenomena in geological samples. Most of the tools we need to investigate these possibilities simply don't exist yet. We're like investigators trying to solve a mystery using techniques that haven't been invented. But perhaps the most intriguing evidence for ancient intelligence lies not in what we can measure, but in what we can't explain. Earth's history contains numerous puzzles that mainstream science struggles to address satisfactorily. The Cambrian explosion, where complex life forms appeared suddenly in the fossil record with no apparent precursors. The precise mathematical relationships found in certain geological formations. The unexpected sophistication of early biological systems that seem too complex to have evolved randomly. Each of these mysteries has conventional explanations, but those explanations often require us to accept remarkable coincidences or invoke processes that we've never observed operating in the present day. The alternative possibility that some of these phenomena might reflect the activities of ancient intelligence is rarely considered, not because the evidence contradicts it, but because the implications are so profound that most researchers prefer not to engage with them. The psychological barriers to accepting the possibility of prehuman intelligence are enormous. Our entire cultural narrative is built on the assumption that we represent the pinnacle of evolution on Earth. We see ourselves as the first species to develop language, art, science, and technology. This belief shapes not just our scientific theories, but our religious traditions, our philosophical frameworks, and our sense of purpose in the universe. Acknowledging that intelligence might have existed before us doesn't diminish our achievements, but it does place them in a very different context. Instead of being the first to ask deep questions about existence, we become the latest in a potentially long line of conscious beings who have grappled with the mystery of their own awareness. Instead of being unique, we become part of a pattern that might repeat throughout cosmic history. This shift in perspective could actually be profoundly liberating. If intelligence is a recurring phenomenon rather than a one-time accident, it suggests that consciousness might be a fundamental feature of the universe rather than an unlikely fluke. It implies that the questions we ask about meaning, purpose, and our place in existence might have been explored by countless other minds throughout the vast expanse of time. The search for ancient intelligence also raises fascinating questions about communication across geological timescales. If previous civilizations existed, did they attempt to leave messages for future intelligent species? How would such messages be encoded to survive hundreds of millions of years of geological change? What medium could preserve information across such vast spans of time? Traditional materials like stone, metal, or even diamond would eventually be destroyed by geological processes, but information might be preserved in more subtle ways. Patterns in crystal lattices that encode data at the atomic level. Genetic sequences inserted into simple organisms that could survive and reproduce across eons. Mathematical relationships embedded in the distribution of certain minerals or the structure of ancient reef systems. The possibility of discovering such messages presents both exciting opportunities and sobering responsibilities. If we found evidence that previous intelligent beings had tried to communicate across time, what would they be trying to tell us? Would their messages contain warnings about dangers they encountered, insights about the nature of consciousness and reality, instructions for avoiding the mistakes that led to their disappearance? The cyclical nature of intelligence on Earth, if it exists, might follow patterns we're only beginning to recognize. Complexity in natural systems often exhibits recurring cycles, with periods of growth, stability, decline, and renewal. Ecosystems go through predictable phases of succession. Star formation follows cyclical patterns within galaxies. Even consciousness itself might be subject to cosmic rhythms that operate on time scales far beyond human experience. If intelligence does emerge cyclically on planetary scales, each iteration might face similar challenges and opportunities. The physics of the universe remains constant, so intelligent beings separated by hundreds of millions of years might still discover the same fundamental principles. The mathematics underlying reality doesn't change, so ancient civilizations might have developed geometric and algebraic insights that we're still working toward. This possibility suggests that our current scientific revolution might be following pathways explored long before us. The quantum mechanics we're discovering, the relativity we're mapping, the complexity theory we're developing, all of these might be rediscoveries of knowledge that was once commonplace among beings who lived when life on Earth was still simple and primitive by our standards. The implications extend to our understanding of evolution itself. We typically think of evolution as a process that moves from simple to complex, from primitive to advanced. But if intelligence has emerged multiple times throughout Earth's history, evolution might be more cyclical than linear. Complexity might arise, reach peaks that we can barely imagine, then simplify again as conditions change or civilizations make different choices about their development. This cyclical model suggests that intelligence might be less about accumulating knowledge and more about learning to work in harmony with natural cycles. The most successful civilizations might be those that recognize their place in larger patterns and choose to evolve in ways that support rather than disrupt the planetary systems that sustain all life. As we drift deeper into these contemplations, the boundaries between science and philosophy begin to blur. The questions we're exploring touch on fundamental issues about the nature of consciousness, the meaning of intelligence, and the purpose of existence itself. They invite us to consider possibilities that stretch far beyond our current understanding while remaining grounded in the evidence that Earth's rocks and fossils continue to reveal. The search for ancient intelligence becomes a search for perspective on our own brief moment of awareness in the cosmic story. Whether or not previous civilizations existed, the questions we're asking expand our vision of what's possible and challenge us to think more deeply about our responsibilities as conscious beings in a universe full of mystery and wonder. The quest to understand these ancient mysteries has led scientists to examine some of the most unusual geological formations on our planet. Deep beneath the surface, in mines that reach kilometers into the Earth's crust, workers have occasionally discovered objects that seem to defy conventional explanations. Perfectly spherical metallic balls embedded in rock formations that predate known civilization by millions of years. Grooved stones with mathematical precision that natural processes struggle to explain. These discoveries sit in an uncomfortable space between mainstream science and speculation. Most researchers approach them with healthy skepticism, proposing natural mechanisms that could account for their unusual properties. Mineral precipitation, they suggest, can sometimes create remarkably regular shapes. Pressure and heat can forge symmetries that appear artificial but arise from purely geological processes. Yet, doubt lingers. The precision of some formations challenges our understanding of what natural forces can achieve. When nature creates order, it typically does so through processes we can observe and replicate. But some of these ancient artifacts display organizational principles that seem to require directed intelligence, even if we can't identify the directing force. This uncertainty reflects a broader challenge in studying deep time. The further back we peer into Earth's history, the less familiar the world becomes. Continental positions were different. Atmospheric composition had distinct characteristics. Ocean chemistry followed patterns unlike anything in our modern experience. Life itself operated according to different rules, with biological processes that have no contemporary analogs. In this alien landscape of the distant past, we must be careful about applying our current understanding of how things work. The bacteria that dominated early Earth weren't simply primitive versions of modern organisms. They were sophisticated chemical engineers, capable of transforming their environment in ways that fundamentally altered the planet's trajectory. These microscopic beings learned to split water molecules, releasing oxygen that poisoned most existing life while enabling entirely new forms of complexity. The Great Oxygenation Event, as scientists call this transformation, represents one of the most dramatic examples of biological engineering in Earth's history. Simple organisms didn't just adapt to their environment. They rebuilt it according to their metabolic needs. The process took millions of years, but its effects were so profound that they created the conditions necessary for all subsequent complex life. This historical precedent raises fascinating questions about what more complex organisms might have achieved given similar timescales. If bacteria could terraform a planet, what might multicellular intelligence accomplish over hundreds of millions of years? The possibilities stretch far beyond our current technological capabilities. Consider the problem of energy. Modern civilization depends on burning fossil fuels, a process that releases carbon dioxide and other byproducts into the atmosphere. But biological systems demonstrate far more elegant solutions. Photosynthesis captures solar energy with remarkable efficiency while producing oxygen as a beneficial side effect. Advanced civilizations might have developed technologies that work with similar principles, harnessing environmental energy flows without creating pollution or waste. Such technologies would leave very different traces than our industrial processes. Instead of carbon emissions and toxic residues, we might find evidence of enhanced biological productivity, unusual patterns in ancient ecosystems that suggest systematic management rather than random evolution, mineral deposits that indicate controlled chemical processes operating over geological timescales. The search for these alternative technological signatures requires interdisciplinary collaboration between geologists, biologists, chemists, and physicists. Each discipline brings different tools and perspectives to the investigation. Geologists read the stories written in rock layers. Biologists trace the evolution of life through genetic and fossil evidence. Chemists analyze the molecular signatures left behind by ancient processes. Physicists explore the fundamental forces that might have been harnessed by unknown technologies. Recent advances in analytical chemistry have opened new possibilities for detecting ancient technological activity. Mass spectrometry can identify trace elements at concentrations measured in parts per billion. Isotope analysis can reveal subtle signatures of nuclear processes that occurred millions of years ago. Organic geochemistry can distinguish between naturally occurring compounds and synthetic molecules that might have been produced by directed intelligence. These tools are revealing patterns in ancient rocks that previous generations of scientists couldn't detect. Unusual concentrations of rare earth elements in formations where they shouldn't naturally occur. Organic compounds with structures that seem too complex to have formed through random chemical processes. Isotope ratios that suggest nuclear reactions took place under controlled conditions rather than through natural radioactive decay. Each discovery adds another piece to a puzzle that remains frustratingly incomplete. The evidence is tantalizing but ambiguous. Natural processes can create remarkable complexity and unexpected patterns. Distinguishing between sophisticated geology and ancient technology requires extraordinary care and rigorous analysis. The challenge is compounded by the vast timescales involved. Chemical signatures that might clearly indicate technological activity when fresh become increasingly difficult to interpret as they age. Organic molecules break down and recombine. Metals oxidize and form new compounds. Even nuclear isotopes eventually decay into different elements, erasing the signatures of their creation. This degradation of evidence over time creates a detection horizon, beyond which even the most advanced technologies might become invisible. The horizon varies depending on the type of evidence, but for most traces of technological activity, it extends only a few million years into the past. Beyond that threshold, we enter a realm where only the most durable signatures might survive, and those would be so altered by geological processes that their original nature would be nearly impossible to determine. Yet within this detection horizon, intriguing anomalies continue to surface. Deep drilling projects designed to study Earth's geological history have encountered layers of sediment with unusual characteristics. Some contain microscopic structures that resemble manufactured objects more than natural formations. Others show chemical compositions that suggest rapid, systematic changes in environmental conditions. These discoveries are forcing scientists to expand their thinking about what constitutes evidence of intelligence. Traditional archaeology looks for tools, buildings, and other obvious artifacts of human activity. But intelligence operating on geological timescales might express itself in far subtler ways. Systematic modifications to ecosystem development, guided evolution that produces biological innovations ahead of their expected timeline, environmental management so sophisticated that it appears to be natural process. The possibility of biological intelligence operating at planetary scales opens up entirely new categories of evidence to consider. Modern genetics reveals that organisms can exchange genetic material across species boundaries through horizontal gene transfer. Bacteria routinely share genetic innovations, allowing beneficial traits to spread rapidly through entire ecosystems. Advanced intelligence might have learned to direct these processes, using genetic engineering to shape biological development according to long-term plans. Such biological technologies might be detectable through careful analysis of evolutionary patterns in the fossil record. Innovations that appear simultaneously in unrelated species. Genetic sequences that seem too complex to have evolved through natural selection alone, ecosystem changes that suggest coordinated responses to environmental challenges rather than random adaptive responses. The study of ancient DNA is beginning to reveal surprising complexity in early biological systems. Genetic sequences that were thought to be relatively recent innovations are turning up in much older organisms. Regulatory mechanisms that control gene expression appear to have been sophisticated from very early in evolutionary history. The molecular machinery that enables life seems to have reached remarkable levels of complexity much sooner than traditional evolutionary models would predict. These findings don't necessarily indicate the presence of ancient intelligence, but they do suggest that biological systems might be capable of far greater sophistication than we previously imagined. The boundary between natural evolution and directed development becomes increasingly difficult to define as we discover more about the complexity that exists at the cellular and molecular levels. The implications extend beyond purely scientific questions. Fundamental issues about consciousness and intelligence itself. If biological systems demonstrate capabilities that approach what we consider technological, where do we draw the line between natural and artificial? What distinguishes conscious design from unconscious optimization processes that produce similar results? These philosophical questions become practical concerns when we consider the possibility of encountering intelligence that operates according to principles we don't yet understand. Our assumptions about how intelligence manifests are based on our own limited experience as individual conscious beings who use external tools to manipulate our environment. But consciousness might take forms that are so different from our own that we wouldn't recognize them even if we encountered direct evidence of their activities. The search for ancient intelligence thus becomes a search for expanded definitions of consciousness itself. Instead of looking only for beings like ourselves, we might need to consider the possibility of collective intelligence, distributed awareness, or forms of consciousness that operate through mechanisms we haven't discovered. Such intelligence might leave traces that we're already observing but not interpreting correctly. The ocean floors hold particular promise for this expanded search. Marine sediments preserve chemical records spanning hundreds of millions of years, and the deep ocean environment protects these records from many of the geological processes that destroy evidence on land. If ancient intelligence was primarily aquatic, or if it operated through biological systems that thrived in marine environments, the evidence might still be detectable in deep-sea cores. Recent oceanographic expeditions have retrieved sediment samples that contain puzzling features, layers of material that seem to have been deposited too rapidly to result from normal sedimentation processes, chemical signatures that suggest systematic processing of seawater on scales that dwarf any known biological activity, microscopic structures that appear to be organized in ways that natural processes don't typically produce. These discoveries are still being analyzed and debated within the scientific community. The ocean environment creates unique conditions that can produce unexpected geological formations. Hydrothermal vents, underwater volcanic activity, and deep-sea chemical processes can create complex patterns that might superficially resemble the products of intelligence. Distinguishing between sophisticated geology and ancient technology requires detailed analysis using multiple independent methods. But the possibility remains that some of these oceanic anomalies might represent evidence of intelligence that operated in environments and through mechanisms completely foreign to our terrestrial experience. Aquatic intelligence might have developed technologies based on fluid dynamics, pressure manipulation, and chemical processes that take advantage of the unique properties of water. Such technologies would leave very different traces than the solid-state electronics and mechanical systems that characterize our own technological development. The search continues, driven by curiosity about our planet's hidden history and by the profound implications that ancient intelligence would have for our understanding of consciousness, evolution, and our own place in the cosmic story. Each new analytical technique opens additional windows into the deep past. Each unusual discovery raises new questions about the nature of intelligence and the forms it might take. Whether or not we ultimately find convincing evidence of pre-human civilization, the search itself is expanding our vision of what's possible. It's challenging us to think more broadly about intelligence, more deeply about time, and more humbly about our own brief moment of awareness. In Earth's vast and mysterious history, the questions we're exploring may not have clear answers, but they're transforming how we think about consciousness, evolution, and the remarkable planet we call home. In seeking traces of ancient intelligence, we're also discovering new aspects of our own nature and our connection to the deep rhythms of geological and biological change that continue to shape our world. The mysteries surrounding potential ancient intelligence have led researchers to examine patterns that exist at the very foundations of life itself. Within the genetic code that governs all biological systems, scientists have begun to discover sequences that seem remarkably sophisticated for their supposed evolutionary age. These molecular arrangements display organizational principles that challenge our understanding of how complexity develops over time. The genetic machinery that enables life to function operates with precision that rivals our most advanced technologies. DNA replication systems demonstrate error correction capabilities that exceed the reliability of human-engineered computers. Protein folding mechanisms solve computational problems that challenge our most powerful supercomputers. These biological systems achieved their sophistication billions of years ago, when life was supposedly simple and primitive. This paradox raises uncomfortable questions about the trajectory of biological development. If the fundamental mechanisms of life were already remarkably advanced when they first appeared, what does this tell us about the nature of intelligence and organization in natural systems? The conventional view suggests that complexity emerges gradually through random mutations and natural selection. But the molecular evidence reveals systems that seem too sophisticated to have arisen through undirected processes. Consider the ribosomes that exist in every living cell. These molecular machines translate genetic information into proteins with extraordinary precision. They contain hundreds of components that must work together in perfect coordination. The probability of such complex machinery arising spontaneously approaches zero. Yet these systems appear to have existed since the earliest stages of life on Earth. Recent discoveries in molecular biology have revealed additional layers of complexity that weren't apparent to earlier generations of researchers. Epigenetic regulation systems that control gene expression, RNA interference mechanisms that fine-tune cellular responses, molecular motors that transport materials within cells with mechanical efficiency that exceeds human engineering. Each new discovery reveals additional sophistication in biological systems that were once considered relatively simple. The implications extend beyond individual cellular mechanisms to the organization of entire ecosystems. Ecological networks display emergent properties that suggest coordination at scales far beyond what individual organisms could achieve through random interactions. Forest networks connected through fungal root systems share resources and information across vast distances. Marine ecosystems maintain chemical balances that require precise coordination between countless different species. These natural networks demonstrate information processing capabilities that approach what we might consider technological. Trees and forests can communicate warnings about insect attacks. Bacterial colonies can coordinate responses to environmental threats. Even simple organisms like slime molds can solve complex optimization problems, finding the most efficient paths through complicated environments. The boundary between biological intelligence and technological capability becomes increasingly blurred as we discover more about the sophisticated information processing that occurs throughout the natural world. What we once attributed to simple chemical reactions turns out to involve complex computational processes. What appeared to be random biological activity reveals underlying patterns of organization and coordination. This expanded understanding of natural intelligence opens new possibilities for interpreting unusual patterns in the geological record. Formations that seem too organized to result from random processes might represent the activities of biological intelligence operating at scales and through mechanisms we're only beginning to recognize. Ancient ecosystems might have achieved levels of coordination and environmental management that we're still learning to identify. The search for such evidence requires us to look beyond conventional archaeological approaches. Instead of seeking artifacts in the traditional sense, researchers are learning to recognize signatures of systematic biological activity, patterns in mineral distribution that suggest directed chemical processes, fossil assemblages that indicate ecosystem management rather than natural succession, genetic sequences that appear in the fossil record ahead of their expected evolutionary timeline. These investigations are revealing anomalies that don't fit comfortably within conventional biological theory. Evolutionary innovations that appear too rapidly to result from gradual natural selection. Ecosystem changes that suggest coordinated responses to environmental challenges. Biological structures that demonstrate engineering principles not typically associated with random evolutionary processes. The challenge lies in distinguishing between sophisticated natural processes and potential evidence of directed intelligence. Biology is capable of remarkable complexity and coordination without conscious guidance. But some patterns in the ancient record seem to suggest systematic modification of biological and geological processes in ways that natural mechanisms struggle to explain. The time frames involved in these investigations stretch human comprehension to its limits. Biological processes that might have operated over millions of years could have achieved transformations that dwarf anything in our experience. Ecosystem management projects spanning geological ages could have reshaped entire continents. Biological engineering programs could have guided evolutionary development along pathways that seemed natural but were actually directed. The evidence for such large-scale biological intelligence remains circumstantial and highly debated. Most scientists prefer explanations that rely on known natural processes, even when those explanations require remarkable coincidences or invoke mechanisms that operate far beyond observed parameters. The alternative possibility that some biological patterns might reflect directed intelligence challenges fundamental assumptions about the nature of evolution and consciousness. Yet the questions persist, driven by accumulating evidence that biological systems are far more sophisticated than traditional theories suggest. The molecular machinery of life demonstrates capabilities that approach conscious design. Ecological networks display coordination that resembles technological systems. Evolutionary patterns sometimes suggest guidance rather than random development. These discoveries are forcing scientists to reconsider basic assumptions about the relationship between consciousness and biological activity. Perhaps intelligence in biological systems is more common than we've recognized. Maybe the capacity for directed activity emerges naturally in complex biological networks. The boundary between conscious and unconscious activity might be far less clear than we've assumed. The implications extend to our understanding of our own place in biological history. If intelligence has emerged multiple times in different forms throughout Earth's history, our current technological civilization represents just one expression of a more general phenomenon. Consciousness might be a recurring feature of complex biological systems rather than a unique accident that happened only once. This perspective transforms how we think about progress and development. Instead of seeing ourselves as the pinnacle of evolutionary achievement, we become participants in ongoing processes that have been operating for billions of years. Our technologies might be rediscoveries of principles that biological systems have been using since life began. Our artificial intelligence projects might be attempts to replicate capabilities that already exist in natural networks. The search for ancient intelligence thus becomes a search for our own biological heritage. By investigating the possibility that intelligence has existed in various forms throughout Earth's history, we're also exploring the deeper nature of consciousness and its relationship to the biological processes that sustain all life. The questions we're asking about the past are simultaneously questions about our own nature and potential future development. The geological record continues to yield surprises that challenge conventional interpretations of Earth's biological history. Recent excavations have uncovered fossil formations that display organizational patterns typically associated with conscious design. These structures appear in rock layers that predate the supposed emergence of complex intelligence by hundreds of millions of years. The formations consist of mineral deposits arranged in geometric patterns that natural processes rarely produce. Crystalline structures aligned in precise mathematical relationships. Sedimentary layers that suggest systematic modification rather than random deposition. These patterns appear too organized to result from purely geological forces, yet they exist in rocks formed long before any known intelligent life. Traditional geology explains such formations through complex interactions between chemical, physical, and biological processes operating over vast timescales. Mineral precipitation can sometimes create remarkably regular patterns. Biological activity can influence sediment deposition in ways that produce systematic arrangements. The interaction between these forces can generate structures that appear designed even when they result from natural processes. But some patterns stretch these explanations to their limits. Formations that display mathematical relationships found in advanced engineering. Structural arrangements that seem to serve functions that natural processes wouldn't require. Organizational principles that suggest systematic planning rather than random development. The investigation of these anomalies requires sophisticated analytical techniques that can distinguish between natural and potentially artificial processes. Electron microscopy reveals structural details that weren't visible to earlier generations of researchers. Chemical analysis can identify trace elements that indicate specific formation processes. Isotope studies can determine the age and origin of materials with unprecedented precision. These analyses are revealing complexity in ancient geological formations that wasn't apparent using traditional methods. Microscopic structures that resemble manufactured components. Chemical compositions that suggest controlled synthesis rather than natural mineral formation. Organizational patterns that appear to follow engineering principles rather than geological processes. The interpretation of these findings remains highly controversial within the scientific community. Most researchers prefer explanations that rely on known geological and biological mechanisms, even when those mechanisms must be stretched to account for unusual patterns. The alternative possibility that some formations might represent evidence of ancient technological activity challenges fundamental assumptions about Earth's history. The controversy reflects deeper philosophical issues about the nature of evidence and interpretation in scientific research. How do we distinguish between sophisticated natural processes and potential artifacts of intelligence? What level of organization and complexity is required before we must consider the possibility of conscious design? These questions don't have clear answers, but they're essential for understanding how to interpret unusual patterns in the geological record. The debate is complicated by our limited understanding of what ancient technologies might have looked like. Our assumptions about technological development are based on our own relatively brief experience with industry and engineering. But intelligence operating over geological timescales might have developed approaches to technology that we can't imagine. Consider the possibility of technologies based on biological rather than mechanical principles, living systems that could grow, repair themselves, and adapt to changing conditions. Organic computers that processed information through biochemical rather than electronic mechanisms. Manufacturing systems that worked with natural processes rather than against them. Such biotechnologies would leave very different traces than our mechanical and electronic systems. Instead of metal oxides and synthetic polymers, we might find evidence of modified biological structures. Unusual patterns in fossil ecosystems that suggest systematic management. Genetic sequences that appear to have been engineered rather than evolved naturally. The search for these alternative technological signatures is expanding beyond traditional archaeological methods. Paleontologists are learning to recognize patterns in fossil assemblages that might indicate ecosystem management. Geochemists are developing techniques for detecting trace evidence of biological engineering. Geneticists are analyzing ancient DNA sequences for signs of modification that natural evolution wouldn't produce. These interdisciplinary investigations are revealing aspects of Earth's biological history that don't fit comfortably within conventional evolutionary theory. Innovations that appear too rapidly to result from gradual natural selection. Ecosystem changes that suggest coordinated responses rather than random adaptation. Biological structures that demonstrate engineering principles not typically associated with evolutionary processes. The evidence remains fragmentary and open to multiple interpretations. Natural biological processes are capable of remarkable sophistication and can produce patterns that superficially resemble conscious design. Distinguishing between advanced natural mechanisms and potential evidence of directed intelligence requires extraordinary care and rigorous analysis. But the accumulating anomalies are forcing researchers to consider possibilities that were once dismissed as purely speculative. The sophisticated information processing capabilities demonstrated by biological systems, the coordination that emerges in complex ecological networks, the engineering principles that appear in natural structures. These phenomena suggest that the boundary between biological and technological activity might be far less clear than we've assumed. The implications extend to our understanding of intelligence itself. If biological systems can achieve technological capabilities through natural processes, what distinguishes conscious design from unconscious optimization? Perhaps intelligence emerges naturally in complex systems and expresses itself through mechanisms we're only beginning to recognize. This expanded definition of intelligence opens new possibilities for interpreting Earth's deep history. Instead of looking only for evidence of beings like ourselves, we might need to consider forms of consciousness that operate through biological rather than technological mechanisms, intelligence that works with natural processes rather than against them, awareness that expresses itself through ecosystem management rather than industrial development. The search for ancient intelligence thus becomes a search for expanded understanding of consciousness and its relationship to the biological processes that sustain life. By investigating unusual patterns in Earth's geological and biological history, we're also exploring fundamental questions about the nature of intelligence and its role in shaping the development of complex systems. Whether or not we ultimately find convincing evidence of pre-human technological civilization, the investigation is expanding our appreciation for the sophistication that exists throughout the natural world. It's revealing capabilities in biological systems that approach what we consider technological. It's challenging us to think more broadly about intelligence and more deeply about our own relationship to the biological networks that sustain all life on Earth. The questions we're exploring about ancient intelligence are simultaneously questions about the future of consciousness and technology. As we develop artificial intelligence systems and biotechnology capabilities, we're perhaps following pathways that have been explored before by intelligence operating through different mechanisms and on different time scales. Understanding these possibilities might help us make better choices about our own technological development and our relationship to the biological systems that sustain our planet. The quest to understand these ancient possibilities has led researchers into realms that challenge our most basic assumptions about how intelligence might manifest across cosmic time. When we consider the sheer magnitude of Earth's history, we begin to appreciate just how limited our perspective truly is. We're examining 4.5 billion years of planetary development through the lens of a species that has existed for less than 300,000 years and has possessed advanced technology for barely 2 centuries. This temporal myopia affects everything about how we interpret the evidence around us. We assume that intelligence must follow the same developmental pathways we've experienced. We expect technology to leave behind the same kinds of traces our civilization produces. We search for consciousness that operates according to the same principles that govern our own awareness. But what if these assumptions are fundamentally limiting our ability to recognize what we're actually looking for? Recent developments in complexity science have revealed that sophisticated organization can emerge through processes that don't require conscious direction. Networks of simple agents following basic rules can generate behaviors that appear purposeful and coordinated. These emergent phenomena occur throughout nature, from the flocking patterns of birds to the synchronized flashing of fireflies to the collective problem-solving abilities of ant colonies. But emergence works in both directions. Just as simple systems can generate complex behaviors, complex systems can sometimes organize themselves in ways that appear simple from the outside. Advanced intelligence might learn to work so efficiently with natural processes that its activities become virtually indistinguishable from purely natural phenomena. The most sophisticated technologies might be those that leave no obvious technological signature at all. This possibility transforms our approach to searching for ancient intelligence. Instead of looking for disruptions to natural systems, we might need to search for patterns that suggest natural systems have been enhanced or optimized beyond what random processes typically achieve. Ecosystems that display mathematical relationships found in advanced engineering. Geological formations that seem to solve optimization problems. Biological networks that demonstrate information processing capabilities that exceed what evolutionary theory predicts. The challenge lies in developing analytical frameworks that can distinguish between sophisticated natural processes and potentially enhanced natural processes. This requires understanding natural systems at levels of detail that push the boundaries of current scientific knowledge. We need to know what purely random geological and biological processes can achieve before we can recognize patterns that might indicate something more. The investigation has led to surprising discoveries about the capabilities of natural systems operating over geological timescales. Bacterial communities that can systematically alter the chemistry of entire ocean basins. Geological processes that can create structures displaying precise mathematical relationships. Evolutionary mechanisms that can produce innovations at rates that seem to exceed what random mutation and natural selection should allow. These discoveries don't necessarily indicate the presence of ancient intelligence, but they do reveal that natural processes are capable of far greater sophistication than traditional scientific models suggest. The boundary between natural and artificial becomes increasingly difficult to define as we learn more about the organizational capabilities that exist throughout the natural world. The implications extend beyond questions about Earth's past to fundamental issues about the nature of intelligence and consciousness. If natural systems can achieve technological capabilities through biological and geological processes, what distinguishes conscious design from unconscious optimization? Perhaps intelligence is a more common feature of complex systems than we've recognized, emerging naturally whenever information processing capabilities reach certain thresholds of sophistication. This expanded understanding of intelligence opens new possibilities for interpreting unusual patterns in the geological and biological record. Formations that seem too organized to result from random processes might represent the expression of intelligence operating through mechanisms we don't yet understand. Biological innovations that appear ahead of their evolutionary timeline might indicate systematic modification of natural development processes. The search for such evidence requires interdisciplinary collaboration that brings together expertise from multiple scientific fields. Geologists contribute understanding of how rock formations develop over time. Biologists provide insights into evolutionary processes and ecosystem dynamics. Chemists analyze the molecular signatures left behind by ancient processes. Physicists explore the fundamental forces that might have been harnessed by unknown technologies. This collaborative approach is revealing patterns that weren't apparent when each discipline worked in isolation. Chemical signatures that make sense geologically but seem unusual from a biological perspective. Biological patterns that fit evolutionary theory but create geological formations that appear engineered. Physical processes that explain individual phenomena but collectively suggest systematic modification of natural systems. The interdisciplinary perspective is also revealing the limitations of our current analytical capabilities. Many of the questions we're asking require measurement techniques that don't yet exist. We need instruments capable of detecting quantum-level modifications to ancient materials. We need analytical methods that can distinguish between natural and potentially artificial processes operating over millions of years. We need theoretical frameworks that can integrate findings from multiple disciplines into coherent interpretations. The development of these capabilities is driving advances in scientific instrumentation and methodology. New forms of mass spectrometry that can detect trace elements at unprecedented sensitivity levels, advanced imaging techniques that can reveal microscopic structures in ancient materials, computational methods that can model complex processes operating over geological timescales. These technological advances are opening new windows into Earth's deep history, revealing details that weren't accessible to previous generations of researchers. Each new analytical capability brings the possibility of discovering evidence that has been hidden in plain sight, waiting for instruments sensitive enough to detect it and theories sophisticated enough to interpret it. The investigation is also revealing the profound challenges involved in preserving information across geological timescales. Chemical signatures degrade and change. Physical structures are altered by pressure and heat. Even the most durable materials eventually succumb to the relentless forces of geological change. The detection horizon for most forms of evidence extends only a few million years into the past, beyond which even advanced technologies might become invisible. This limitation creates a fundamental asymmetry in our search for ancient intelligence. We're looking for evidence of activities that might have occurred hundreds of millions of years ago using analytical techniques that can reliably detect technological signatures spanning only a few million years. It's like trying to read a book that has been exposed to fire, flood, and centuries of weathering, with most pages completely destroyed and the remaining fragments barely legible. Yet, within these constraints, intriguing possibilities continue to emerge. Patterns in the geological record that suggest systematic modification of natural processes. Biological innovations that appear to have been guided rather than randomly evolved. Chemical signatures that indicate controlled synthesis rather than natural mineral formation. Each discovery adds another piece to a puzzle that remains frustratingly incomplete, but increasingly intriguing. The philosophical implications of this research extend far beyond questions about Earth's past. If intelligence has emerged multiple times throughout our planet's history, consciousness might be a more fundamental feature of the universe than we've assumed. Instead of being a rare accident that occurred only once, awareness might be a natural consequence of complexity that emerges whenever conditions allow sufficient information processing capabilities to develop. This perspective transforms our understanding of our own place in the cosmic story. Rather than being the first intelligent beings in our corner of the universe, we might be participants in ongoing processes of consciousness development that have been operating for billions of years. Our technologies might be rediscoveries of principles that have been explored before. Our questions about existence and meaning might be variations on themes that have been contemplated by countless minds throughout deep time. The search for ancient intelligence thus becomes a search for expanded understanding of consciousness itself. By investigating the possibility that awareness has taken multiple forms throughout Earth's history, we're also exploring fundamental questions about the nature of mind and its relationship to the physical processes that sustain complex systems. These investigations are revealing that consciousness might be far more diverse and widespread than our human-centered perspective suggests. Intelligence might emerge through biological rather than technological pathways. Awareness might operate through collective rather than individual mechanisms. Consciousness might express itself through environmental management rather than industrial development. The implications extend to our thinking about the future of intelligence and technology. As we develop artificial intelligence systems and explore biotechnology applications, we might be following developmental pathways that have been explored before by forms of consciousness operating through different mechanisms. Understanding these possibilities could help us make more informed choices about our own technological development and our relationship to the biological systems that sustain life. The investigation continues, driven by curiosity about our planet's hidden history and by the profound questions that ancient intelligence would raise about the nature of consciousness, evolution, and our place in the universe. Each new analytical technique opens additional possibilities for detecting traces of intelligence that might have operated through mechanisms we don't yet understand. As we reach the end of our journey through deep time, we find ourselves with more questions than answers, and perhaps that's exactly as it should be. The search for ancient intelligence has revealed something profound about the nature of knowledge itself. Every analytical technique we develop opens new mysteries. Every discovery challenges assumptions we didn't even realize we held. Whether or not civilizations existed before the dinosaurs, the investigation has transformed our understanding of what's possible. We've discovered that biological systems possess capabilities that rival our most advanced technologies. We've found that natural processes can create patterns of remarkable sophistication. We've learned that consciousness might be far more diverse and widespread than our human perspective suggests. The geological record continues to whisper its secrets, encoded in chemical signatures and mineral formations that span billions of years. Some patterns remain unexplained, sitting quietly in the margins of scientific understanding, waiting for new analytical techniques or theoretical frameworks that might reveal their true nature. Perhaps the most important discovery is humility. Earth's history stretches so far beyond human experience that we must remain open to possibilities we can barely imagine. Intelligence might take forms we wouldn't recognize. Technology might operate through principles we haven't discovered. Consciousness might emerge through mechanisms that challenge our deepest assumptions about awareness and design. As you drift toward sleep tonight, let these possibilities settle gently in your mind. In the vast expanse of deep time, mysteries await that could transform our understanding of intelligence, consciousness, and our own place in the cosmic story of